It was an hour ago. Anyway.
We're better. Definitely.
More diligent.
Yeah.
Okay, good. What we want to do today, first of all, questions on project. Do we have any project questions? Yes?
Is there a certain option to create that SPSS data file?
It's written up in the description someplace there where it's talking about section 3, but it's something like the file menu, file information, something along those lines. So what you do is set up the blank SPSS file, and that puts out a description then of your variables, the types of variables and so forth that I can then cross-check.
You have the like problem-solving web thing on there. Do we use that too? Or?
No.
Okay, because I was like, how do we do that?
Yeah, I put that out there. At previous semesters I've talked about that a little bit, trying to show how things fit together. This was kind of an experiment this time to not really do too much with it. You certainly don't need to do that. What you saw in the example didn't have that in it,
right.
And what's in the example is perfectly adequate.
Okay, and then the bias discussion, that's not in your example, that's in the
Beginning of section 3, there was this discussion of bias there. It doesn't have to be very long.
right.
In fact, oftentimes it isn't separated out. They talk about how they're going to collect data and the potential bias as a result of that.
Does each question have a confounding variable?
In the past, I've always had at least one confounding variable for each question, and I decided not to even discuss that this semester. If you can come up with one, that's fine, but I'm not going to count off if you don't have them either. What I found is that particularly at this level, we've got so much stuff coming at us. Confounding variables are variables that confuse things, and I found that the things that confuse the most is students. And so at this point, it's an important concept. It's something that you'll need to use if you get later on in your program. But at this point, it's probably not critical that we talk about it.
So just ignore it?
Yeah, you can ignore it. Anything else? Okay, what I want to do then is we're going to talk about Chapter 9. How many read sections 1 through 3 of Chapter 9? I see you were all diligent for showing up, but kind of fell flat on that one.
I think we're all banging on that high school.
Well, I'm going to have to go over the material anyway. So, we're going to go through those 3 sections. We'll talk about most of the material in there. We'll have a couple of problems for you to work on, and we'll get the solutions to those problems to you before you leave today. So you'll be able to take a look at that. So, let's get started. Chapter 9 is about sampling distributions. And what we want to do is just get an introduction to this. We're not talking about all the different situations yet. We're not getting into a lot of details yet, but we're going to kind of get the idea. Okay? Okay, there's our population. So a population is that thing that we're interested in finding out about. And remember that if we could measure every individual in the population, we wouldn't be in this class at all, would we? We wouldn't need statistics if we could get at that population. So this is the thing that we either is too expensive, too difficult, or impossible to actually measure. And so we're going to try to infer something about this population. So this is things that are unknown. In that population, there are characteristics that we're interested in. Those characteristics, when we measure them, can be quantitative, ordinal, or categorical. But in any case, there will be certain things that we're going to measure for each instance. For example, if we're interested in a quantitative characteristic, we're going to be interested in a mean and a standard deviation, mu and sigma. For the cases where we're talking about categorical, and in this class, if it's ordinal, we'll treat it as if it were categorical. So in this class, anything that's categorical, we're going to be talking about P, which is a proportion for that population. So an example might be is we talk about the population of voters who voted yesterday. P might be the proportion that voted for McCain. So P is the proportion in a particular category. And that is a characteristic of the population. Okay. And we call these things parameters. The other thing we're going to do is we're going to treat them as if they are constant. Now remember we talked about the fact that the population, for example, the population of the United States is constantly changing. But if I were to look at this P and say this P is the proportion of males in the United States population. Now we know that the population is changing continually, and even over a matter of days or even weeks, do you think that that proportion of males changes very much? Probably not much at all. It may change out in 5th, 6th, 7th decimal place kinds of things, but in general it is effectively constant. What would happen if I was trying to make an inference about a population parameter and it was constantly changing? Okay. Yeah. Worse than skewed even. Skew actually implies that there is something there and that there is this trailing off. In this case, it's a lot worse than even skewed because essentially I couldn't get it. It's a moving target. It's basically like trying to hit a moving target with your eyes closed. If you happen to hit that moving target with your eyes closed, it has nothing to do with skill or anything else. It's just pure dumb luck. Okay? And it really has nothing to do with where the target actually was. So in that case, if this isn't relatively constant, we really can't do anything. So we're assuming that these things are constant parameters. They're the things that we're shooting for. They're the things that we're trying to find out about. Now we've already talked about the idea that we take a sample from this. That sample results in an actual measurable information. And what I'm going to suggest is that on Monday, when we were flipping coins, each of you took a sample from a population. In that case, the population was all possible coin flips. One of the first things we talked about was the number of heads in that sequence of 10 coin flips. So what you did was you took a series of 10 coin flips, you took some n, and n in that case was equal to 10, and you counted the number of heads. If we had then taken that number of heads and divided it by 10 so we get a proportion, we'd get a proportion of heads in the particular sequence that you got. And we would have calculated a p hat. P in this case is the proportion of heads in the population. I think we all agreed the proportion of heads in the population was 1/2, right? 0.5. And each individual had some p hat that ranged from 0 to 1. You know, most people didn't have 0. We didn't have 1s, but there was a lot that were around the 0.5, 0.4, 0.6 range. Is that correct? So I think you guys came up with the ones that was really nicely, tightly distributed.